Welcome to the Deep Dive. We take complex topics, sift through the sources, and, well, pull out the key insights to get you up to speed, fast.
That's the plan.
Today we're diving into something kind of invisible but absolutely essential. It powers pretty much everything digital around you, your phone, your computer, even the AI making headlines.
We're talking about memory hierarchy design for system-on-chip architectures, so FLIs.
Exactly. Sounds technical, I know, but stick with us.
Yeah, because this stuff, it's foundational. It really dictates how fast your devices run, how long the battery lasts, how, secure everything is.
Our mission today is to cut through that complexity.
Right.
Find those aha moments for you.
And give you a clear grasp of why this matters so much.
Because it really does shape your whole tech experience. This careful balancing act, memory speed, how much memory, the cost. It's not just some detail for engineers. It directly impacts performance, battery life, even how big the device physically is. PPA efficiency, right? Power, performance area.
Precisely. And for the really demanding stuff, AI, machine learning, high-performance computing, getting this right is absolutely critical, non-negotiable, really.
So what's the big hurdle they face?
Well, the classic problem, one that's been around a while, is the memory wall.
Ah, yes, the memory wall.
Think of it like this. Your processor is like a super fast brain ready to calculate instantly.
Huh?
But the data it needs is like a book in a huge, slightly slow library. The memory...
So the brain is just waiting.
Constantly waiting. Processor speeds have shot up way faster than memory access speeds. So the processor spends more and more time just idling, twiddling its thumbs, waiting for data.
That's the bottleneck.
That's the bottleneck. And memory hierarchy design. That's the clever strategy, the direct response to try and tear down that wall or at least work around it.
Okay, so in this deep dive, what are we unpacking?
We'll get into the different levels of memory, how they actually coordinate, the big design challenges architects wrestle with daily.
And the new solutions popping up.
And the cutting-edge stuff, absolutely. You'll see it's not just about raw speed. It's like a really smart, layered approach to deal with these fundamental limits.
All right, let's start peeling back those layers then. Where do we begin?
Okay, so at its heart, a memory hierarchy is basically a structured setup of different storage types. Each has its own strengths and weaknesses, its own trade-off.
Like a pyramid.
Exactly like a pyramid. At the very top, you've got incredibly fast memory, but it's also really expensive and tiny in capacity.
Got it.
As you go down the pyramid, the memory gets slower, but it also gets much cheaper, and you get vastly more space.
So the whole system is trying to balance that.
The whole point is to balance speed, cost, and capacity. To make sure the CPU gets the data it needs as quickly as possible most of the time, without breaking the bank or making the chip enormous.
Okay, so take us to the very top, the peak of the pyramid.
Right inside the CPU itself, like intimately close, are the registers.
Registers.
Yeah. Think minuscule, ultra-high-speed memory spots. Access is almost instantaneous, maybe 0 clock cycles, but they are incredibly small. Maybe 16 bits, 64 bits.
So just holding what the CPU is working on right this second.
Pretty much. It's the CPU's immediate scratch pad. Active data, active instructions.
Okay, tiny scratch pad. What's just below that?
Directly below registers, you find cache memory. This is crucial. It's a small, fast buffer, physically very close to the CPU.
And its job?
Its job is to store temporary copies of data that the CPU uses often, data pulled from the next level down, main memory. By keeping copies close, it drastically cuts down the time it takes to fetch that data again.
Like keeping your most used tools right on your workbench.
Perfect analogy. Instead of walking back to the storage shed every single time you need that wrench.
Makes sense. And you mentioned cache isn't just one thing. It has layers too.
Precisely. It's usually tiered for even better efficiency. You typically have L1 cache level 1, smallest, fastest, right next to the CPU core. Sometimes it's even split into one part for instructions and one for data, so the CPU can grab both simultaneously.
Okay, L1, then?
Then L2 cache, a bit larger, a bit slower than L1. Often each CPU core gets its own L2.
And L3.
And finally, L3 cache. This is the largest and slowest of the cache levels, and it's usually shared among multiple CPU cores on the chip. It acts as a sort of last resort before having to go out to the much slower main memory.
And what's cache actually made of? What makes it so fast?
Cache is typically built with SRAM static random access memory. SRAM is fast because it doesn't need constant refreshing to hold its data, unlike the main memory type. But that also makes it more expensive and less dense.
Okay, so registers and cache are the super fast but relatively small top layers. What's the main work area? the system's primary memory.
That would be main memory, what most people just call RAM.
RAM, right.
This is where the bulk of the currently running programs and their data reside. Much, much larger than cache, but also, naturally, slower to access.
And RAM itself has different types. You mentioned SRAM for cache.
Right. The other main type used for main memory is DRAM dynamic RAM. DRAM is much denser than SRAM, meaning you can pack more storage into the same space, and it's significantly cheaper.
But there's a catch.
The catch is it's dynamic. It needs to be periodically refreshed, have its electrical charge topped up, otherwise it loses the data. Kind of like a leaky bucket you have to keep refilling.
Okay, DRAM for main memory because it's dense and cheaper. SRAM for cache because it's faster.
You got it.
And then way down at the bottom of the pyramid, the long-term storage.
Finally, yes, you have secondary storage. This is your hard disk drive, your HDD, or more commonly now, your solid-state drive, your SSD.
For keeping files, photos, the OS.
Exactly. Stuff you need to keep even when the power is off, non-volatile storage. It offers huge amounts of space, but accessing it is orders of magnitude slower than accessing RAM or cache. Think of it like the archive library basement.
So looking at the whole pyramid, you can really see those trade-offs playing out.
Absolutely. Speed versus capacity versus cost. Registers. Lightning fast, tiny, expensive per bit. Secondary storage. Enormous, cheap per bit, but slow as molasses.
And the hierarchy tries to give you the best illusion.
It tries to give you the illusion of having a huge amount of memory that's almost as fast as the registers. It works by cleverly moving data up and down these levels, trying to anticipate what the CPU will need next. It's a constant optimization game.
What makes this whole system work? You mentioned it anticipates what's needed. How?
This is the really fascinating part. The core principle that makes the entire hierarchy effective is something called the principle of locality.
Yep.
Yeah. It's this fundamental observation about how programs behave. They tend to access the same small chunks of data and instructions over and over again. And they tend to access data locations that are physically close to each other in memory.
So programs don't just jump around randomly all the time.
Not usually, no. If they did, the hierarchy wouldn't help much. Locality is kind of the silent hero that enables all this.
Okay, tell me more about these types of locality.
Well, there are two main kinds. First is temporal locality. Temporal meaning time. If a program accesses a piece of data now, there's a very high probability it will access that same piece of data again very soon.
Okay, so the cache keeps recently used stuff nearby.
Exactly. The hierarchy exploits this by keeping recently accessed data in those faster, higher levels like the cache, basically betting you'll ask for it again shortly.
And the other type?
The other is spatial locality. Spatial meaning space or location. If a program accesses a particular memory address, it's highly likely to access other addresses nearby very soon.
Okay. Like reading sequential instructions in a program.
Precisely. Or accessing elements sequentially in an array. This is why when the system fetches data from main memory into the cache, it doesn't just bring one byte, it brings a whole chunk called a cache line or cache block.
Yeah.
Maybe 64 bytes.
So it grabs the neighbors too, figuring you'll probably need them.
That's the idea. It's like if you go to the filing cabinet for one document, you might as well grab the whole folder because chances are you'll need the other papers in it too.
And the impact of this locality thing on actual speed.
Oh, it's profound. Huge. Programs written to have good locality ones that access data predictably and reuse data often run significantly faster. Why? Because most of the time, the data they need is already waiting in the fast cache, a cache hit.
And bad locality.
Bad locality means lots of cache misses. The program keeps asking for data that isn't in the cache, forcing the system to go all the way down to slower main memory or even secondary storage. The performance difference can be staggering. Like, you could have two algorithms that do the exact same mathematical calculation, say matrix multiplication, but one is structured to access memory with good locality, and the other isn't. The one with good locality might run 10, 20 times faster just from arranging the memory accesses better.
Wow. 20 times faster just from how you access data.
It's a massive lever, which means this isn't just a hardware problem.
Right. Software developers need to think about this too.
Absolutely. Writing locality-aware code, structuring your algorithms and data layouts to maximize temporal and spatial locality is just as crucial for performance as the hardware design itself. It's really a co-design challenge. Hardware and software have to work together.
Okay, so we have the layers, we have locality. You mentioned cache hits and misses. Let's dig into cache performance. performance, because that seems like where the real action is.
It really is. Cache is arguably the most complex and dynamic part. So yeah, let's talk metrics. First, a cache hit. That's the goal. The CPU asks for data, and bam, it's right there in the cache. Super fast access. Success. A cache miss, on the other hand, is when the data is not in the cache. The CPU asks, the cache shrugs, and now we have to go hunting in a slower level, like L2, L3, or main memory. That incurs a time penalty. Minimizing misses is key.
And I guess not all misses are created equal. Are there different reasons why the data wouldn't be there?
That's a great point. Yes, there are different categories or flavors of misses. First are compulsory misses, sometimes called cold start misses. These happen the very first time a piece of data is ever accessed. It has to be missed because it wasn't in the cache to begin with. They're kind of unavoidable.
Okay, the first time is always a miss. What else?
Then you have capacity misses. These occur simply because the cache isn't infinitely large. The program needs more data than the cache can hold, so older data gets kicked out to make room, even if it might be needed again later. The cache is just full.
Makes sense. Too much stuff, not enough space.
Right. Then there are conflict misses. These are a bit trickier. They happen because of how the cache is organized. Sometimes, multiple different blocks of main memory are only allowed to map to the same specific spot in the cache.
So even if the cache isn't full overall, two frequently used items might fight over the same single location.
Exactly. They keep evicting each other. It's like having two essential tools that only fit in the same single slot on your workbench. Very frustrating, and it hurts performance.
Okay, compulsory, capacity, conflict, any others?
In systems with multiple processors or cores, you also get coherence misses. This happens when one core modifies data in its cache, but another core still has an old, outdated copy of that same data. The second core's copy has to be invalidated or updated, causing a miss if it tries to read the stale data. We'll get more into coherence later. It's a big topic.
Got it. So, based on hits and misses, how do we measure cache effectiveness?
The main metrics are hit rate, the percentage of memory accesses that result in a cache hit. Higher is better, obviously.
And the flip side is the miss rate.
Yep. Miss rate is just 1 minus the hit rate, the percentage of accesses that miss. Then there's the miss penalty. This is the extra time it takes to handle a miss, the time to go fetch the data from the lower, slower level.
And that's why we have multiple cache levels, L1, L2, L3, to soften that penalty.
Precisely. An L1 miss might be caught by the slightly slower but larger L2, which has a much smaller miss penalty than going all the way to main memory. L2 misses might get caught by L3. It reduces the average miss penalty.
Okay. What else? Bandwidth. Latency.
Yes, bandwidth is crucial. That's the rate at which data can be moved between memory levels, usually measured in bytes per second. Super important for things like graphics or AI that chew through data. And latency is the total time delay from when data is requested until it's actually delivered.
And these interact, right? Like a bigger cache might reduce misses, but maybe increase latency slightly.
Exactly. It's all interconnected. Making the cache larger might improve the hit rate, fewer capacity misses, but could potentially make accessing the cache itself slightly slower just due to its physical size and complexity, or it might increase power consumption.
So it's always a trade-off, a multi-dimensional puzzle for the designers.
Always. They're constantly juggling these factors to find the sweet spot for the specific chip's purpose.
You mentioned conflict misses happening because of how the cache is organized. How does the cache decide where to put data? What are the strategies?
Good question. There are 3 main mapping strategies. The simplest is direct mapped cache.
Direct mapped.
Here, each block of main memory has exactly one specific predetermined line in the cache where it can go. No other choice. Calculation is super simple. Memory address modulo cache size tells you the line.
So very easy to find where data should be.
Incredibly fast to check. You only need to look in one spot. But the big downside is
conflict misses. If 2 important pieces of data happen to map to the same exact spot,
bingo. They'll constantly kick each other out, even if the rest of the cache is empty. Performance can suffer badly in those cases. It's simple, but potentially brittle.
Okay, that sounds maybe too simple. What's the opposite extreme?
The opposite is a fully associative cache. Here, a block of data from main memory can be placed in any available line within the entire cache. Total flexibility.
So that avoids conflicts misses completely.
It does. It generally gives the best possible hit rate because it uses the cache space most efficiently. But the massive drawback is complexity and cost. To find a piece of data, you have to compare the requested address tag against the tag of every single line in the cache, all at the same time.
Wow, okay. That sounds hardware intensive, like searching every drawer in a huge filing cabinet simultaneously.
Exactly. It requires a lot of parallel comparison hardware, consumes more power, and is slower to access than direct mapped. So you rarely see large, fully associative caches.
So if direct mapped is too rigid and fully associative is too complex, there must be a middle ground.
There is, and it's the most common approach used in practice. Set associative cache.
Set associative.
This is the pragmatic compromise. The cache is divided into a number of sets. A block from main memory still maps to one specific set using a simple calculation like direct mapped. But once it gets to that set, it can go into any of the lines within that small set. Maybe there are 2 lines per set, 2A set associative, or 4, or 8, or 16.
So it reduces the chance of conflict compared to direct mapped, because there are a few slots within the set.
Exactly. It significantly reduces conflict misses compared to direct mapped. And checking for data only requires comparing against the tags within that one specific set. Say, 8 comparisons for an 8-way set associative cache, which is much, much simpler and faster than checking the entire cache like in fully associative.
That makes sense. A good balance.
It really hits that sweet spot between hit rate and complexity cost. That's why you typically see set associative designs for L1, L2, and L3 caches in modern CPUs.
Okay, now within a set associative cache, if the set is full and new data needs to come in, you still have to kick something out from that set. How does it decide which line to evict?
Ah, yes. That's the job of the cache replacement policy. This is another critical piece for performance. The goal is to make the smartest guess about which block currently in the set is least likely to be needed again soon.
Makes sense. What are the common strategies here?
Well, the simplest is first in, first out. FIFO. Just like it sounds. The block that has been in the set the longest, the first one in, is the first one to get kicked out when space is needed.
Easy to implement, I guess.
Very easy, but often not very effective. It doesn't consider how frequently or how recently a block was actually used, just how long it's been sitting there. It might kick out something important just because it arrived early.
Yeah, sounds like cleaning out the fridge based only on expiration date, not what you actually use daily.
Good analogy. A much more common and generally effective policy is least recently used, LRU.
OU.
This policy tracks when each block in the set was last accessed. When an eviction is needed, it kicks out the block that hasn't been touched for the longest time.
That seems smarter. It adapts to what's actually being used.
It does. LRU performs very well for many real-world programs because it leverages that temporal locality principle we talked about. If you haven't used something in a while, you probably won't use it again soon. The downside is it's more complex to implement than FIFO because you need hardware to keep track of the usage order for all the blocks in the set.
Okay, LRU sounds good, but complex.
Yeah.
Anything else? Maybe based on frequency.
Yes. There's also least frequently used, LFU. This policy keeps account of how many times each block in the set has been accessed. It evicts the block with the lowest access count.
So it prioritizes things that have been popular over time.
Exactly. It's good for workloads where access patterns are stable, but it's even more complex to implement than LRU because you need counters for every cache line. And it has a potential pitfall called cache pollution. Yeah, imagine a block gets accessed a lot very early on, but then is never needed again. LFU might keep it around for a very long time just because its initial count was high, potentially preventing newer, more relevant data from entering the cache.
I see. So again, no single perfect answer. The best replacement policy depends on the workload.
Absolutely. It depends on the specific access patterns of the applications the chip is designed to run. Designers might even use variations or hybrid policies. It's another knob to tune in that complex optimization puzzle.
Okay, we've covered reading from cache. But data also gets written back. How does the cache handle writes? And how does it make sure the main memory eventually gets updated? You can't have inconsistencies.
Critical point. Managing writes correctly is essential for data integrity. This is handled by cache write policies. There are 2 main approaches.
Okay, what's the first one?
The first is called write-through. With write-through, whenever the CPU writes data to a cache line, that data is written simultaneously to both the cache and the next level down, like main memory.
Both places at once.
Both places at once. The big advantage is simplicity and consistency. Main memory is always up to date. If the power fails, you haven't lost any committed writes.
But the disadvantage sounds like performance. Every write has to wait for the slower main memory.
Exactly. Every single write operation incurs the latency of writing to the slower memory level. This can create a significant write bottleneck and generates a lot more traffic on the memory bus.
Okay, consistency, but potentially slow writes. What's the alternative?
The alternative is write back. This is generally more common for performance-critical caches like L1. With write-back, when the CPU writes data, it's written only to the cache line initially.
Only the cache, so main memory becomes out of date.
Temporarily, yes.
Uh-huh.
The cache controller marks that modified cache line using a special flag called a dirty bit. The actual write to main memory is delayed until later. Specifically, it happens only when that dirty cache line needs to be evicted from the cache to make room for new data.
Ah, so it saves up the writes and does them only when necessary.
Pretty much. The huge advantage is much faster write operations from the CPU's perspective because it only has to talk to the fast cache. It also significantly reduces the traffic to main memory because multiple writes to the same cache line only result in one final write back when it's evicted.
But the downside seems obvious. What if the power goes out before that dirty data gets written back?
That's the main risk, yes. Potential data loss on power failure if the dirty data hasn't been flushed. It also adds complexity to the cache controller, which now has to track dirty bits and manage the write-back process.
So another fundamental trade-off. Write-through gives you integrity, write-back gives you performance.
That's the core choice. Which one you use depends heavily on the system's requirements. How critical is immediate consistency versus maximizing write speed? Often you might see write-through used for certain types of data and write-back for others.
Okay, now let's throw another complication in. Modern sockets have multiple processor cores, right? Each potentially with its own private cache, but they might need to access the same data in main memory.
Yes, and this introduces a massive challenge: cache coherence.
Coherence, keeping everyone's view consistent.
Exactly. Imagine Core A reads a piece of data into its private cache. Then Core B reads the same piece of data into its private cache. Now, what happens if Core A writes to its copy?
Uh-oh. Core B still has the old, outdated version?
Precisely. Core B now has stale data. If it uses that stale data, you get incorrect results. This is the cache coherence problem. We need mechanisms to ensure that all cores maintain a consistent, unified view of shared memory.
So what needs to happen? How do systems enforce this?
Systems need to enforce two key properties. First, write propagation. When one core writes a value, any subsequent read by any core must eventually return that written value. Second, write serialization. Writes to the same memory location by different cores must appear to happen in some single consistent order to all cores.
Okay. Sounds essential but complicated. How do they actually do this?
Through cache coherence protocols. These are sets of rules and messages that the caches and memory system follow. The two main families of protocols are snooping protocols and directory-based protocols.
Snooping, like eavesdropping.
Kind of. In snooping protocols, all the caches are connected to a shared bus. Whenever a core performs a read or write to shared data, a message about that operation is broadcast over the bus. Every other cache controller snoops on this bus traffic.
Okay. And what do they do when they see something relevant?
If a snooping cache sees a broadcast indicating that a block it holds is being modified by another core, it knows its own copy is now stale and must invalidate it, mark it as unusable, or perhaps request the updated data. Think of it like a group chat where everyone instantly sees all messages and reacts accordingly.
That sounds like it works, but maybe gets noisy with lots of cores, all that broadcasting.
That's exactly the limitation. Snooping works well for systems with a relatively small number of cores, maybe up to 8 or 16. But as you add more cores, the shared bus becomes saturated with all the broadcast coherence messages.
Yeah.
It doesn't scale well.
So for larger systems, you need something else.
Right. That's where directory-based protocols come in. Instead of broadcasting everything to everyone, these protocols use a central directory. This directory keeps track of which caches currently hold a copy of each block of memory, and in what state. Example, shared, exclusive, modified.
So it's like a central librarian knowing who has checked out which book.
Excellent analogy. When a core wants to read or write a block, it first checks with the directory. The directory then knows exactly which other specific caches need to be notified or have their state changed. It sends targeted point-to-point messages only where needed.
Much less broadcast traffic. More scalable.
Much more scalable for systems with many cores, like dozens or hundreds. The trade-off is the overhead of maintaining and accessing the directory itself, but it avoids the bus bottleneck of snooping.
You mentioned a specific protocol example earlier, MESI. Is that snooping or directory-based?
MUSI is a classic, widely used snooping-based protocol. It's an acronym for the 4 states a cache line can be in. Modified. This cache has the only valid copy, and it's dirty, different from main memory. Exclusive. This cache has the only copy, but its clean matches main memory. Shared. This cache has a clean copy, and other caches might also have clean copies. And invalid, this cache line's data is not valid.
So the cache lines constantly transition between these states.
Exactly. Based on the read and write operations happening locally and the messages being snooped from the bus, each cache line follows strict rules to transition between M, E, S, and I states. This intricate dance ensures that, for example, if a core wants to write to a line currently in the shared state, it must first send out messages to invalidate all other shared copies before it can transition its own copy to modified.
Wow. It sounds like a very complex state machine running constantly.
It is. But it's fundamental to making multi-core processors work correctly. And the evolution from simple snooping like MSI towards more sophisticated directory protocols directly reflects the need to scale coherence as SoCs pack in more and more processing power.
Okay, beyond pure performance, designing these hierarchies for SoCs involves some really tough constraints. Let's talk about power consumption and energy efficiency. That seems huge, especially for mobile devices.
Oh, absolutely paramount. Many SoCs live in battery-powered devices, so minimizing power draw is critical for usability. Even in data centers, power consumption translates directly to electricity bills and cooling costs. Plus, too much power concentrated in a small area generates heat, which can damage the chip or require bulky, expensive cooling.
So designers are constantly thinking about performance per watt.
Constantly. It's a primary design goal. You want the most computational power for the least energy consumed.
How do they achieve that specifically in the memory system, which is accessed so often?
Several techniques. Using specialized low-power memory components is one, like LPDDR RAM, low-power double data rate, which is common in smartphones.
Okay.
Then there's dynamically adjusting the memory system's operating point. Dynamic voltage and frequency scaling, DVFS, allows the system to lower the memory's voltage and clock speed when the full performance isn't needed, saving significant power.
Scaling it down when idle or doing simple tasks.
Exactly. And even more aggressively, power gating can completely shut off power to entire sections of the memory hierarchy that are not currently in use, like turning off the lights in unused rooms.
So it's not just about picking low power parts, but actively managing power during operation.
It's a combination of static design choices and dynamic management. Every milliwatt counts when you're trying to maximize battery life or minimize heat.
Another huge constraint must be the physical space on the chip itself. Area optimization on die. Silicon isn't cheap or unlimited.
You bet. Chip area directly translates to manufacturing cost. The larger the chip die, the fewer chips you get per silicon wafer, and the higher the chance of a defect ruining a chip. So minimizing area is critical for economics.
And memory takes up a lot of that space, especially cache.
Memory, particularly SRAM-based caches, can consume a very significant portion of the total soft die area. So making the cache bigger to improve performance directly increases the chip's size and cost.
So designers have to be really clever about saving space.
They do. Tricks include things like minimizing the number of bits used for data where possible. For instance, using fixed point arithmetic instead of full floating point if the application can tolerate slightly less precision. This reduces the size of registers, data paths, and memory storage. Also, resource sharing, where a single piece of hardware logic, like an adder or multiplier, is reused for multiple different operations at different times rather than duplicating it. And sometimes, for larger caches, they might choose to use embedded DRAM, EDRAM. It's denser than SRAM, meaning it takes less area for the same capacity, even though it might be slightly slower or require refresh.
So again, it's that trade-off. Performance versus area versus cost. You might sacrifice a little speed to make the chip smaller and cheaper.
Every single design decision involves navigating these competing requirements. There's rarely a single best choice, only the best compromise for the target product.
It's not just the memory components, but how they talk to each other, like the pathways, communication and interconnect architectures. Even fast memory is useless if the road is clogged.
Exactly. The interconnect fabric that connects the CPU cores, caches, main memory, and other peripherals is absolutely vital. If the interconnect bandwidth or latency becomes the bottleneck, then optimizing the memory itself doesn't help much. You just shift the bottleneck.
So how do they design fast, efficient interconnects?
Several approaches. We mentioned multi-channel memory architectures earlier. Instead of one path to main memory, you have multiple parallel channels, dramatically increasing the total available bandwidth. Think of adding more lanes to a highway.
Right. widening the pipe.
And pipelining is used heavily, not just in the CPU, but in the memory access path, too. Breaking down the complex process of a memory request into smaller stages allows multiple requests to be in different stages of processing simultaneously, improving overall throughput, like an assembly line for data requests.
The car wash analogy again?
The car wash analogy, it works well. While one request is fetching data, the address for the next request is already being calculated.
And the underlying technologies themselves get faster, too.
Absolutely. The move from DDR3 to DDR4, then DDR5, and LPDDR variants keeps increasing the raw speed and bandwidth of the DRAM interfaces. And specialized tech like high bandwidth memory, HBM, stacks memory chips vertically